Here is a question that should not be as hard to answer as it is. What is at the end of the universe? Not the observable universe. We'll get to that distinction, and it matters enormously. I mean the actual universe. All of it. Everything that exists. If you could travel in a straight line forever, never stopping, never turning, what would you eventually reach? What is at the furthest possible point from where you're standing right now? Is there a wall, a void, a boundary where space simply ends and something else begins? Or does it go on forever? And if so, what does forever actually mean when you're talking about physical space? This is one of the oldest questions in all of human thought. Philosophers wrestled with it in ancient Greece. Cosmologists are wrestling with it right now, with data from the most powerful telescopes ever built. And the honest answer, the scientifically rigorous, evidence-based current best answer, is one of the most unsettling things modern physics has ever produced. We don't know. Not in the way that we don't know what dark matter is made of, where we're close and getting closer. Not in the way we don't know whether there's life elsewhere in the universe, where the absence of evidence isn't evidence of absence. We don't know what's at the end of the universe in a deeper, more fundamental sense, in the sense that the question itself may be malformed. That asking what is at the edge of the universe may be like asking what is north of the North Pole. That the universe may be structured in such a way that the question simply doesn't have a meaningful answer. Or it may have an answer so strange, so counterintuitive, so alien to everyday experience, that when you hear it, your first instinct will be to reject it. This video is about both possibilities. We're going to go to the edge of what we can observe, to the very limits of telescopic vision, where the most distant light ever detected is just barely reaching us after traveling for 13.8 billion years. And then we're going to go further, beyond what we can see, beyond what we can measure, into the territory of models and mathematics and cosmological inference, where the answers get progressively stranger and the certainty gets progressively thinner. And at the end of all of that, we're going to stand at the furthest conceptual edge of what physics currently understands, and look at what's there. What's there is not nothing. What's there is one of the most extraordinary ideas in the history of human thought. Let's start with what we actually know. Chapter 1. The edge of what we can see. Before we can talk about what's at the end of the universe, we need to be precise about something that most people conflate without realizing it. The observable universe and the universe are not the same thing. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. The universe is everything, the whole thing, including all the parts from which light hasn't reached us yet, either because it hasn't had enough time or because the expansion of space is carrying those regions away faster than light can cross the distance. These are profoundly different concepts, and the distinction between them is the key to understanding everything that follows. Here's how the observable universe works. The universe is 13.8 billion years old. Light travels at approximately 300,000 kilometers per second, the fastest anything can move through space. So in 13.8 billion years, light can travel 13.8 billion light years. Simple enough. The observable universe should, therefore, have a radius of 13.8 billion light-years. Except it doesn't. The observable universe has a radius of approximately 46.5 billion light-years, not 13.8 billion. 46.5 billion. How? If the universe is only 13.8 billion years old, how have we received light from sources 46.5 billion light-years away? Because space itself has been expanding the entire time the light was traveling. When a photon sets off from an extremely distant galaxy shortly after the Big Bang, that galaxy is relatively close. The universe is young, and everything is compressed. But as the photon travels toward us, the space it's moving through is stretching. The universe is expanding in every direction, constantly. By the time the photon finally reaches us, the galaxy that emitted it has been carried by that expansion to a location far further away than it was when the photon departed. The photon has been traveling for 13.8 billion years, but the source has been moving away the whole time, carried by the expansion of space itself, which has no speed limit the way objects moving through space do. So the most distant light we can detect, the cosmic microwave background, the faint thermal glow of the universe when it was only 380,000 years old and first became transparent, was emitted from matter that is now approximately 46 billion light-years away. That matter has been receding from us for 13.8 billion years, carried by expansion, and it is now at that distance. The observable universe, then, is a sphere 93 billion light-years in diameter, centered on Earth, not because Earth is special or central, but because the observable universe is always centered on wherever you are observing from. Any point in the universe has its own observable universe, its own sphere of space from which light has had time to arrive. Our sphere happens to be centered here. Everything inside that sphere, every galaxy, every star, every wisp of gas and dark matter, is in principle detectable. We can receive light from it. It is part of our observable universe. Everything outside that sphere is, in the most complete sense, beyond our horizon. Light from those regions has not had time to reach us. It has been traveling toward us since the Big Bang, but it isn't here yet, and in some cases, for regions beyond what's called the Hubble radius. The expansion of space is carrying them away from us faster than the speed of light, which means that light emitted from those regions right now will never reach us. The gap between us and them is widening faster than light can close it. Those regions exist. They are real. They contain matter and energy and structure. But they are permanently, irrevocably beyond our observational reach. This is the first and most important boundary in the story of the universe's edge, the cosmic horizon. The edge not of the universe, but of the universe we can ever access. Now let's talk about what we see when we look toward that horizon, because what we see there is extraordinary. The most distant confirmed individual galaxies ever observed sit at redshifts above 13, meaning the light from them has been stretched by the expansion of the universe to more than 14 times its original wavelength by the time it reaches us. These are galaxies we are seeing as they existed when the universe was less than 400 million years old, less than 3% of its current age. The James Webb Space Telescope, which began operations in 2022, has pushed this frontier further than any previous instrument. In its first years of operation, Webb detected galaxy candidates at redshifts approaching and possibly exceeding 16, objects we are observing as they existed when the universe was only about 250 million years old. The universe at that epoch was not supposed to contain the kind of massive, structured galaxies Webb is finding. Models of galaxy formation are being revised in real time as Webb looks further and further back, towards the cosmic horizon, towards the edge of the observable universe, toward the moment when the first stars and galaxies switched on and the universe lit up for the first time. That moment, the epoch of rionization, when the first ultraviolet radiation from the first stars began ionizing the neutral hydrogen fog that had filled the universe since 380,000 years after the Big Bang, is one of the great observational frontiers of modern cosmology. Webb is beginning to see into it, and what it finds there will tell us not just about the first galaxies, but about the conditions in the early universe that set the stage for everything that followed. But even Webb has a limit. The cosmic microwave background, the oldest light in the universe, emitted 380,000 years after the Big Bang, is the absolute observational wall. We cannot see through it with light-based telescopes, because before 380,000 years after the Big Bang, the universe was opaque. The photons from that era didn't travel freely. They scattered off the dense, hot plasma of the early universe like light scattering off fog. We see the CMB as a perfect, nearly uniform glow from every direction in the sky. The thermal afterimage of that fog at the moment it cleared. But we cannot see what was behind it, at least not with photons. Gravitational waves potentially could. Gravitational waves pass through matter without interacting with it. They are ripples in space-time itself, not electromagnetic radiation. Gravitational waves generated in the first fractions of a second after the Big Bang, before the universe was opaque, would still be propagating today. Detecting them, which requires instruments vastly more sensitive than anything currently in operation, would be equivalent to seeing the universe before the CMB, seeing through the fog to the very earliest moments. This is one of the great observational goals of 21st century physics. And if we achieve it, the edge of our observational universe will push back further still, closer to the bang itself, to the first microseconds, to conditions so extreme that the physics governing them was fundamentally different from anything we encounter today. But even then, even if we could see all the way back to the first instant, we would still be inside our observable universe. We would still not have answered the question, what lies beyond the horizon? What is outside the sphere? What is the universe like out there, in the vast, possibly infinite regions of space from which light has not yet arrived? Chapter 2: What the universe is made of, and why that changes. Everything. Before we can talk about what's at the edge of the universe, we need to understand what the universe is. Not just its contents, stars, galaxies, gas, dust, but its fundamental composition. Because the answer to that question is one of the most startling revelations in modern cosmology, and it completely changes how we think about the universe's structure and ultimate fate. The universe, it turns out, is mostly things we don't understand. Specifically, ordinary matter, the stuff made of protons, neutrons, and electrons, the stuff that makes up every atom in every star, planet, and human body, accounts for approximately 5% of the total energy content of the universe. 5%? The remaining 95% consists of two things: dark matter, which makes up about 27%, and dark energy, which makes up about 68%. Dark matter is real. We know this not from detecting it directly. No dark matter particle has ever been conclusively identified in a laboratory, but from its gravitational effects. Galaxies rotate too fast for the gravity of their visible matter to hold them together. There must be additional mass we can't see. Galactic clusters bend light from background objects more than their visible mass accounts for. Gravitational lensing that requires additional unseen mass. The large-scale structure of the universe, the way galaxies cluster into filaments and voids, matches simulations only when an invisible scaffolding of dark matter is included. Something is there. Something with mass. Something that gravitates. Something that shaped the cosmic web. We just don't know what it is. Dark energy is stranger still. In 1998, two independent teams of astronomers studying distant Type 1 supernovae, exploding stars used as standard candles to measure cosmic distances, made an announcement that shook cosmology to its foundations. The universe wasn't just expanding, it was accelerating. The expansion was speeding up. Distant supernovae were dimmer than they should have been if the expansion were decelerating, as gravity, pulling everything back toward everything else, should cause it to. Instead, the supernovae were further away than expected. The expansion was getting faster. Something was pushing the universe apart. Something was working against gravity on the largest scales, driving the acceleration of expansion. That something got the name dark energy, and it has baffled physicists ever since. The leading candidate for dark energy is the cosmological constant, a term Einstein himself introduced into his field equations of general relativity and then, famously called his greatest blunder, having added it to prevent his equations from predicting a dynamic universe before the expansion was discovered. Einstein put the constant in to make the universe static, then removed it when Hubble's observations showed the universe was expanding. But then, in 1998, the accelerating expansion revealed that something very much like a cosmological constant was needed after all, not to hold the universe still, but to explain why the expansion was speeding up. The cosmological constant, in modern terms, is the energy density of the vacuum. Empty space, it turns out, is not actually empty. It has an intrinsic energy, a baseline hum of quantum fluctuations that permeates all of space, even regions with no particles whatsoever. And this vacuum energy has a gravitational effect, but not an attractive one. Its effect is repulsive. It pushes space apart. It is the engine of the accelerating expansion. Why does the vacuum have the energy density it does? Nobody knows. Quantum field theory, our best theory of the subatomic world, predicts a vacuum energy density something like 120 orders of magnitude larger than what we observe. This discrepancy between the theoretical prediction and the measured value is the largest discrepancy between any theoretical prediction and any measurement in the history of physics. It is sometimes called the worst prediction in science. There is something extraordinarily wrong with our understanding of the vacuum. And the vacuum is everywhere. It is the fabric of the universe. But the failure of our prediction doesn't mean we don't know what dark energy does. We know exactly what it does. We've measured it. We've watched it work. And to understand what's at the edge of the universe, we need to understand one particular consequence of dark energy that is so strange it borders on philosophical horror. Dark energy means the universe has a fate, a specific, calculable, deeply unwelcoming fate. Because dark energy is the energy of empty space, and empty space is being created continuously as the universe expands, the total amount of dark energy in the universe is increasing. Not the density. The cosmological constant keeps the energy density of each cubic meter of vacuum constant. But the number of cubic meters of vacuum is growing as expansion creates new space. So the total dark energy grows. And as the total dark energy grows, it drives faster expansion, which creates more space, which creates more dark energy, which drives faster expansion still. It's a runaway process, not a violent runaway. It's been going on for the last 5 billion years, and we haven't noticed in daily life. But on cosmological timescales, it is inevitable and inexorable. The universe is accelerating into a future of increasing emptiness. Galaxies beyond our local group, the gravitationally bound cluster of galaxies that includes the Milky Way and Andromeda, are already receding faster than light due to the expansion of space. In a few billion years, even the nearest clusters will cross our cosmic horizon and disappear from view forever. The night sky will go dark, one galaxy at a time, as the accelerating expansion strips them from our observable universe. In roughly 1 trillion years, a civilization in what is now the Milky Way, merged with Andromeda into the galaxy astronomers have nicknamed Milkomeda, would look out into a sky containing almost nothing. No other galaxies visible, no hint of the cosmic web, no evidence that anything exists beyond the immediate gravitational neighborhood. The universe would appear, to that civilization, small and lonely and almost empty. They would be catastrophically wrong about the size of the universe, but they would have no way of knowing it. This is the long-term consequence of dark energy, the progressive isolation of gravitational islands in an accelerating void. The universe doesn't end with a bang or a whimper. In this scenario, it ends with silence and darkness, each island of matter drifting alone in an expanding sea of vacuum it can neither cross nor see beyond. And crucially, and this is the point that connects back to our central question, this progressive isolation means that the universe beyond our horizon is not only vast, but increasingly inaccessible. Not just now, but forever. The edge of what we can ever know is not fixed. It is shrinking in the most operationally meaningful sense, as dark energy drives more and more of the universe beyond our reach. But for our purposes, for understanding what's at the edge of the universe, dark energy has one additional critical implication that overshadows everything else. Because dark energy is causing the expansion to accelerate, regions of the universe that are currently beyond our observable horizon are getting further away faster. The Hubble radius, the distance at which recession speed equals the speed of light, is not fixed. As the expansion accelerates, it is shrinking relative to our ability to ever receive signals. Galaxies that are currently observable, galaxies whose light is just barely reaching us, will eventually accelerate beyond the horizon. Their light will become too red-shifted to detect. They will disappear from view. The observable universe is not fixed. It is shrinking, not in the sense that its current radius is decreasing, but in the sense that new galaxies will stop being observable over time, and eventually, in the very far future, almost nothing outside our local gravitational group will be visible. The sky will go dark. The universe will become profoundly lonely. But here's the flip side, and this is where we begin to push into what's actually out there, beyond what we see. If the expansion is accelerating, and dark energy is the constant energy density of the vacuum, then the structure of the universe beyond our horizon is almost certainly not fundamentally different from what we see inside it. Dark energy doesn't care whether a region is inside or outside our light cone. The vacuum energy is the same everywhere. The laws of physics are the same everywhere, which means the universe beyond our horizon is almost certainly full of the same things we see inside it: galaxies, stars, dark matter halos, the cosmic web of filaments and voids, more structure, more matter, more of everything we see, extending outward, possibly forever, unless the universe is finite. And that is one of the most important open questions in cosmology. A question we will get to shortly. But first, let's understand what shape the universe is. Because the shape of the universe, in the technical, mathematical sense, is one of the strangest and most counterintuitive concepts in all of science. And it is absolutely central to the question of what's at the edge. Chapter 3. The shape of everything. When we ask what is at the edge of the universe, we're really asking about the geometry and topology of the universe. And those two things, geometry and topology, are different, and both matter. Geometry is about curvature. Topology is about connectivity. You can have a surface with a particular geometry, say flat, but with a topology that connects back on itself, so that what appears to be an infinite flat surface is actually finite and loops around. Think of a video game screen where the character walks off the right edge and appears on the left. Flat geometry, finite connected topology. Let's start with geometry because it's the one we have the most observational evidence for. Einstein's general relativity tells us that mass and energy curve space-time. We've verified this countless times: light bending around massive objects, time running slower in stronger gravitational fields, gravitational waves rippling outward from colliding black holes. Space-time is not a rigid backdrop. It's dynamic. It bends. But the large-scale geometry of the universe, its overall shape on the grandest scales, is not determined by local concentrations of mass. It's determined by the total average energy density of the universe compared to a critical value. If the universe's energy density is exactly equal to the critical density, a specific value determined by the Hubble constant, then the universe is flat, geometrically flat, meaning that on the largest scales, the rules of Euclidean geometry apply. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees, and space extends in all directions without intrinsic curvature. If the energy density is above the critical value, what cosmologists call a closed universe, then the geometry is positively curved, like the surface of a sphere. In a closed universe, if you travel in a straight line long enough, you return to where you started. The universe loops back on itself. Parallel lines converge. The angles of a triangle add up to more. than 180 degrees. And crucially, a closed universe is finite. It has a finite volume, no boundary, and no edge, in the same way that the surface of a sphere has a finite area and no edge. If the energy density is below the critical value, an open universe, the geometry is negatively curved, like a saddle or a hyperboloid. Parallel lines diverge. Triangle angles add up to less than 180 degrees. An open universe in most models is infinite. Now, which one is the universe? The best measurements we have, from the cosmic microwave background, from surveys of large-scale structure, from observations of distant supernovae, tell us that the universe is geometrically flat. The Planck satellite's measurements of the CMB put the curvature parameter within about 0.5% of zero. The universe is flat, to the best precision we can currently achieve. Flat. But here's what that actually means, and what it doesn't mean. It doesn't mean the universe is infinite. Flatness is of geometric property, not a topological one. A flat universe could be infinite, extending outward in all directions without end. Or it could be finite with a flat topology, connected back on itself in a way that a traveler would eventually return to their starting point, but without any intrinsic curvature. What the flatness measurement does tell us is that if the universe is curved, if it's technically closed or open, the curvature radius is so large that it's indistinguishable from flat within the volume of our observable universe. If the universe is a sphere, it's a sphere so vastly larger than our observable bubble that we can't detect the curvature. Like standing on the surface of the Earth and not being able to tell it's curved because the radius is so much larger than your field of view. The current measurements constrain the size of the total universe to be at least several times larger than the observable universe. Some analyses put the lower bound at hundreds of times larger. Inflationary cosmology, the leading theory of the very early universe, generically predicts that the total universe should be vastly, absurdly larger than the observable portion. How much larger? We'll get there in Chapter 5. But before we get there, it's worth sitting with what the flatness measurement is actually telling us, and what it isn't. When the Planck satellite measured the CMB temperature fluctuations to extraordinary precision and derived a curvature parameter within 0.5% of zero, it was measuring the geometry of the observable universe, the portion of space whose light has reached us. The curvature of the full universe could be non-zero, but it would have to be small enough that the difference between the full curvature and flat is undetectable within our horizon. This is a profound limitation. Imagine trying to determine whether the Earth is a sphere by making measurements across an area the size of a living room. Locally, the curvature is so small that you'd measure flat. You'd need to extend your measurements across thousands of kilometers before the curvature became detectable. The observable universe is our living room, the portion of the full universe visible to us. And the full universe may be curved on scales so much larger than our horizon that we simply can't see it. This is why the flatness measurement doesn't settle the geometry question definitively. It tells us the curvature radius is very large. It doesn't tell us it's infinite. A universe with a curvature radius 10 times larger than our observable bubble would be indistinguishable from a flat universe with current data. A universe 1,000 times larger would be even more so. The geometry of the universe, whether it is truly flat, gently closed, or gently open, may be one of the questions that cosmology can never fully answer, regardless of how good our instruments become. Because the answer may lie beyond the horizon, in the unobservable region, permanently out of reach. But before we zoom out to inflation and the multiverse, we need to talk about a possibility that doesn't get enough attention. A possibility that would mean the universe is finite, has a specific size, and has a geometry we might actually be able to detect. The possibility that the universe has a non-trivial topology, that it folds back on itself in a way we could, in principle, observe. Chapter 4: The Universe That Folds Back on Itself. Here's a thought experiment. Imagine you're an ant living on the surface of a cylinder. The cylinder extends infinitely in one direction, but is finite, and connected in the other. If you walk around the cylinder in the finite direction, you return to where you started. If you walk in the infinite direction, you never return. From the ant's local perspective, the surface feels flat. There's no curvature. The ant can't tell, from local geometry alone, that the surface is finite in one direction. The only way to discover the topology, the connectivity, is to actually travel around the cylinder and find yourself back where you started. Or to look across the cylinder and recognize your own back. Now apply this to the universe. If the universe has a non-trivial topology, if it folds back on itself in some direction, then it would, in principle, be possible to see the same object in multiple directions in the sky. Not a reflection, the actual object, with the light that left it traveling in opposite directions around the universe and arriving at our telescopes from different angles. Even more dramatically, if the universe is small enough in some direction that light has had time to travel around it since the Big Bang, we should see matching patterns in the cosmic microwave background. The CMB is not perfectly uniform. It has tiny temperature fluctuations at the level of 1 part in 100,000, which are the imprints of quantum fluctuations in the very early universe that seeded the formation of all large-scale structure. If the universe loops back on itself within our observable horizon, those temperature patterns should appear on opposite sides of the sky as correlated, as matched pairs of circles with identical temperature patterns. This is called the circles in the sky signature, and cosmologists have looked for it. The most famous non-trivial topology candidate is the Poincaré dodecahedral space, a finite, closed topology in which the universe is shaped like a dodecahedron, with opposite faces identified and glued together with a slight twist. In 2003, a French team analyzed the WMA-PCMB data and reported hints of this topology. A suppression of large angle correlations in the CMB that they argued was consistent with a finite universe with the topology of a dodecahedral space. The size of the universe in this model would be roughly 3 to 4 times the diameter of the observable universe. The claim was contested, and subsequent analyses with higher precision data from the Planck satellite did not find compelling evidence for the matched circle signature that would confirm the dodecahedral topology. But they also didn't definitively rule it out. The precision of the measurements is limited, and some topologies would produce signatures too subtle or too large to detect in current data. It's worth pausing to really feel what a finite, multiply-connected universe would mean in practice. Because the intuition most people have, that a finite universe must have an edge, a wall, some kind of boundary you could reach, is completely wrong. Think about it this way. The surface of the Earth is finite. It has a finite area, and yet it has no edge. There is no point on the Earth's surface where you fall off, no boundary beyond which there is nothing. You can walk in any direction forever, and you will never reach an edge. You will simply loop back. The finite surface is closed, boundaryless. A finite universe with a non-trivial topology works exactly the same way, just in 3 dimensions instead of 2. In a Poincare dodecahedral universe, for instance, if you were somehow able to travel fast enough and far enough in a specific direction, you would eventually find yourself approaching what looks like a galaxy you've seen before, from a different angle. You'd be looking at a copy, arriving at the image that left in the opposite direction. In the most extreme case, if the universe were small enough, you could theoretically see yourself, the light that left the back of your head, traveling around the universe and arriving back at your eyes from the front. You would be your own cosmic background object. We don't see this. The universe doesn't appear to be that small. But the topology question remains open for a universe that is finite, and anywhere between a few times to many times larger than our observable bubble. If the repeat image distance is larger than our horizon, we could never see the repetition. The universe could be finite and looping back on itself, and we would have no way of detecting it from where we stand. As of now, the topology of the universe is genuinely unknown. It could be simply connected, extending infinitely in all directions with no loops or identifications. Or it could be multiply connected, finite, folded back on itself, with a topology that a future experiment might detect. The stakes of the answer are enormous. A simply connected, flat, infinite universe has no edge, no end. It just goes on forever in all directions, filled with matter and energy and structure, as far as any physical process could ever reach. An edge would be a meaningless concept. There is no furthest point, because for any point you nominate, there's another point further out. A multiply connected, finite universe has no edge either, just like the surface of a sphere has no edge, but it does have a finite size. Travel far enough in any direction and you come back to where you started. There is no outside. The universe is all there is, and it is finite, and it connects back on itself. Both of these options are deeply strange. Both of them mean that the question, what is at the edge of the universe, has a different kind of answer from what most people expect. Not a wall, not a void, either infinite extension with no edge, or a closed surface with no edge, like the surface of a sphere. In neither case is there a place you could point to and say, there, that's the end. Beyond that, nothing. But there is a third option, and it's the one that cosmology considers most seriously in the current era. The one that comes out of the most successful theory of the early universe ever developed. The one that doesn't just answer what's at the edge of the observable universe, but what's beyond it, far beyond it, in regions of space that may be radically different from our own. Chapter 5: Inflation and the Universe Beyond the Horizon. In 1980, a young physicist named Alan Guth was working on a problem in cosmology that had been bothering theorists for years. Actually, several problems, 3 of them specifically, and they were deeply connected. The first was the horizon problem. The CMB, the thermal afterglow of the early universe, is extraordinarily uniform. In every direction you look, the temperature is almost identical, 2.725 Kelvin, with variations only at the level of 1 part in 100,000. This uniformity is striking, but here's the problem. Regions of the sky on opposite sides of us, regions separated by more than 180 degrees on the sky, were causally disconnected when the CMB was emitted. They were so far apart that no signal, not even light, had had time to travel between them since the Big Bang. They had never been in contact. They couldn't have coordinated their temperatures, and yet they're the same, to 1 part in 100,000. How? The second was the flatness problem. The universe is geometrically flat to extraordinary precision, but flatness is an unstable condition. A universe that starts with even a tiny deviation from perfect flatness will rapidly evolve away from flatness, either collapsing into a closed, curved universe or stretching into an open, curved one. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, it must have started out flat to an extraordinary precision, within roughly 1 part in 10 to the 61st power. That's not impossible, but it requires a fine-tuning of initial conditions that seems deeply unsatisfying as a fundamental explanation. The third was the monopole problem. Grand unified theories, theoretical frameworks that attempt to unify the strong, weak, and electromagnetic forces into a single force at very high energies, predict that the extremely high temperatures of the early universe should have produced enormous numbers of magnetic monopoles, exotic particles that behave like isolated north or south, magnetic poles. We don't see any magnetic monopoles. 0. Where did they go? Guth's solution to all 3 problems was breathtaking in its elegance and audacity. He proposed that in the first tiny fraction of a second after the Big Bang, somewhere between 10 to the minus 36 and 10 to the minus 32 seconds, the universe underwent a period of exponential expansion. Not the gentle, gradual expansion we see today. Explosive, violent, staggering expansion. The kind of expansion in which the universe doubled in size roughly every 10 to the minus 34 seconds, doing so approximately 60 to 100 times in rapid succession. This is inflation. The numbers involved are almost impossible to convey. In the period of inflation, the universe expanded by a factor of at least 10 to the 26th, a billion times its original size. Some models predict even more, starting from a region smaller than a proton and inflating it in a tiny fraction of a second to a size larger than our current observable universe. Let's check the 3 problems. The horizon problem. Before inflation, all of the matter and energy that would become our observable universe was crammed into a tiny region, small enough that every part of it was in causal contact with every other part. The uniformity of the CMB is not a coincidence. It's the thermal equilibrium of a tiny, thoroughly mixed region, inflated to cosmic scales. The flatness problem. Whatever initial curvature the universe had was inflated away. Inflate any curved surface by a factor of 10 to the 26th, and the curvature radius becomes so enormous that the surface appears flat within any observable region. Flatness is a natural, automatic prediction of inflation, not a fine-tuned initial condition. The monopole problem, whatever monopoles were produced before or during inflation, were diluted by the expansion to an undetectable density, roughly 1 per volume, far larger than our observable universe. Inflation solved all three problems in one stroke, and it made predictions that could be tested. The quantum fluctuations that existed in the tiny pre-inflationary region would, under inflation, be stretched to cosmological scales, becoming the seeds of the large-scale structure of the universe. The statistical properties of those stretched fluctuations, their spectrum, their distribution, should be detectable in the CMB. And when the CMB was measured with sufficient precision, beginning with COBE in the early 1990s and reaching extraordinary resolution with WMAP and Planck, the pattern of temperature fluctuations matched the inflationary predictions almost perfectly. Inflation is the most successful theoretical framework in cosmology. It is not proven. We don't have a confirmed detection of primordial gravitational waves, which would be the smoking gun evidence for the energy scale of inflation, but it is taken seriously by the overwhelming majority of cosmologists precisely because it works so well. But inflation's implications for the edge of the universe are what concern us here, because inflation doesn't just solve those three problems. It makes a much larger, much stranger prediction about the structure of the universe beyond our horizon. Here's the problem with inflation. How did it stop? Inflation is driven by a field, the inflaton field, that has a very high energy density. This energy density acts like an extremely powerful version of dark energy, causing exponential expansion. Eventually, the inflaton field rolls down to a lower energy state, releasing its energy as ordinary matter and radiation. The event called reheating, which is essentially the hot Big Bang that standard cosmology describes. Inflation ends. Normal expansion begins. But here's the thing. Quantum mechanics introduces a fundamental randomness into when and where the inflaton field transitions to its lower energy state. At any given point in space, there's a probability per unit time that the field will roll down and inflation will end there. But while inflation is still going, the exponential expansion is constantly creating new space, new regions, where the inflaton field hasn't yet transitioned. And because that expansion is exponential, the new space is being created faster than the local regions are transitioning. Inflation, once started, is almost impossible to stop everywhere at once. In any given region, it eventually ends. But globally, across all of space, it never ends. There are always new regions where inflation is still ongoing, being created by the very expansion that's diluting the regions that have already transitioned. This is called eternal inflation, and it is one of the most profound and most debated ideas in theoretical cosmology. In the picture of eternal inflation, our observable universe, including all 93 billion light-years of it, including all 2 trillion galaxies and their billions of stars, is one bubble in an infinite, eternally inflating background. Our bubble formed when a region of the inflaton field transitioned to its low energy state. That transition was the beginning of our hot Big Bang. Inflation ended locally, and our universe formed. But simultaneously, infinitely many other regions underwent the same transition, forming other bubbles. and the space between the bubbles is still inflating, an eternally expanding background sea of inflation, generating new bubbles continuously, forever. Now let's think carefully about what the space between the bubbles actually is, because this is the part that almost nobody talks about, and it is one of the most genuinely alien things in all of theoretical cosmology. The space between bubble universes is not empty in the way that intergalactic space inside our universe is empty. Intergalactic space has a vacuum energy density, has the residual glow of the CMB, has the occasional wisp of gas, and is expanding at a specific measured rate. The space between bubbles in eternal inflation is inflating, expanding exponentially, at a rate driven by the enormous energy density of the inflaton field, still in its high energy state. The expansion between bubbles is incomparably faster than the expansion inside any bubble. In the time it takes our universe to expand by 1%, the space between bubbles might double, and double again, and double a billion more times. This means that in almost all cases, the bubbles are driven apart faster than they can reach each other. But under some conditions, bubbles formed close enough together can collide before the inflating background separates them, and such a collision would leave an observable scar, a circular ring of anomalous temperature in the cosmic microwave background, the gravitational bruise left by the shockwave of two universes brushing against each other. Cosmologists have actually searched for these collision signatures in the CMB data from WMAP and Planck. Several candidate regions have been examined, and so far none have been confirmed. But the search continues. A confirmed bubble collision signature would be the most extraordinary observational discovery in the history of science. Direct evidence, written in the sky, that another universe exists. This is the multiverse. Not the multiverse of science fiction, not parallel universes where you made a different decision or where history went differently. Something much larger and stranger, an infinite collection of bubble universes, each formed by its own local end of inflation, each potentially with different physical properties, different values of the fundamental constants, different particle physics, different amounts of dark energy. How can different bubbles have different physics? Because in the quantum landscape of string theory, the theoretical framework that attempts to unify all known physics, the vacuum of a universe is not uniquely determined. There are thought to be an astronomically large number of possible vacuum states, each with different properties, each constituting a different version of the laws of physics. Which vacuum state a bubble universe settles into when inflation ends in that region is determined by quantum chance. The string theory landscape estimates somewhere around 10 to the 500 possible vacuum states. That number is so large it is genuinely beyond human comprehension, more than the number of atoms in the observable universe, raised to the power of the number of atoms in the observable universe, and then raised to that power again, many times over. Each of those vacua is a potential universe with its own set of physical laws. In eternal inflation, all of them may be realized. All 10 to the 500 possible physics. An infinite collection of bubble universes, each a cosmos in its own right, each governed by its own version of the laws of nature. The vast majority of these bubble universes would be hostile to life as we know it. The constants would be wrong, the physics would be broken, stars or atoms wouldn't form. Only a tiny fraction would have conditions compatible with complexity, chemistry, biology, observers. We are inevitably in one of those. This is the anthropic principle applied to the multiverse. We shouldn't be surprised that our universe has the constants it does, the ones that allow for stars, planets, chemistry, and us. We couldn't exist to observe a universe that didn't. The fact that we're here making observations is itself a selection effect. Among the infinite bubbles, we are necessarily in one of the ones where physics works for us. Whether this argument is compelling or vacuous, whether the multiverse is a genuine scientific theory or an unfalsifiable metaphysical speculation dressed in mathematical clothing, is one of the great ongoing debates in theoretical physics. We'll return to that debate. But first, let's go further, because eternal inflation and the multiverse are not the deepest possible answer to what's at the edge of the universe. They're nested inside an even larger framework, one that pushes the concept of the universe to its absolute breaking point. And that framework begins with a question that sounds like it belongs in philosophy class, but turns out to be one of the most active areas of theoretical physics. Why is there something rather than nothing? Chapter 6: The Quantum Multiverse. Many worlds and the structure of reality. Let's go back to the question that ended Part 1. Why is there something rather than nothing? It sounds like a philosophy question. It sounds like the kind of question you ask at 3 a.m. after a few drinks, the kind of question that feels profound and unanswerable by design. But it is, in fact, one of the most active and serious questions in theoretical physics. And the answers that physicists have proposed are among the strangest ideas ever entertained by serious, sober, credentialed scientists. Because here's the problem: the eternal inflation picture, the multiverse of bubble universes, each one a cosmos with its own physics, floating in an infinitely inflating background, is a vast and strange answer to the question of what's beyond our observable horizon. But it's still not the deepest answer, because it presupposes something. It presupposes that there is an inflaton field, that there are laws of physics governing it, that quantum mechanics applies, that space-time exists, that the mathematics underpinning the whole picture is real and operative. Where did all that come from? The multiverse of eternal inflation is nested inside a framework. What is that framework nested inside? This is where we encounter the second kind of multiverse, not the one generated by eternal inflation, which is sometimes called the Level 2 multiverse in physicist Max Tegmark's taxonomy, but the one generated by quantum mechanics itself, the Level 3 multiverse, the many worlds interpretation. Here's the background. Quantum mechanics, our most precisely tested theory of nature, describes the world at the subatomic level using a mathematical object called the wave function. The wave function encodes all possible states of a quantum system simultaneously. A particle doesn't have a definite position. It has a superposition of all possible positions, each with a certain probability amplitude. The wave function evolves smoothly and deterministically according to the Schrödinger equation. Then something happens that the theory in its basic form doesn't cleanly describe. You make a measurement. You look at the particle to find out where it is, and suddenly the wave function collapses. All the other possibilities disappear, and the particle is found in one definite location. This collapse is the central mystery of quantum mechanics. It is not described by the Schrödinger equation. It appears to require something outside the theory: Titur, measurement, an observer, a classical apparatus to trigger it. For decades, the Copenhagen interpretation, the standard textbook view, simply said, don't ask what happens before the measurement. The wave function is a calculational tool. The measurement gives you a definite result. That's all physics can tell you. Hugh Everett III disagreed. In 1957, Everett proposed a radical alternative. What if the wave function never collapses? What if the Schrödinger equation is always universally valid, even during a measurement? What would happen then? What would happen is this. When you measure the particle and the wave function should collapse to a definite position, instead the wave function of the entire system, particle, measuring apparatus, your eyes, your brain, the room you're in, the entire universe, evolves into a superposition of all the possible measurement outcomes. In one branch of the wave function, the particle is here. In another, it's there. In another, it's somewhere else. All of these branches are equally real, equally physical, equally described by the mathematics. You, the observer, are also in superposition. You branch along with the particle. In one branch, you see the particle here and record that result. In another branch, you see it there and record that. Both versions of you are real. Both continue to evolve, completely unaware of each other, because the branches decohere. Quantum interference between them becomes unmeasurably small, almost immediately, and each branch evolves as if it were the only one. This is the many worlds interpretation, and it implies that every quantum event, every radioactive decay, every photon interaction, every subatomic process anywhere in the universe, splits the universe into branches. The universe is constantly ramifying, endlessly branching, with every quantum event producing a new fork in the wave function of everything. The number of branches is, in any practical sense, infinite. The total amount of reality, the total content of the wave function of the universe, is incomprehensibly vast, and each branch is a universe in its own right, a complete, consistent, classical-looking world in which the inhabitants cannot perceive the branching and cannot communicate with other branches. What's at the edge of this kind of multiverse? Nothing meaningful. There is no edge to the wave function of the universe. It is not extended in space. It is extended in configuration space, the abstract mathematical space of all possible quantum states of everything that exists. The edge of the many worlds a multiverse is not a location. It's the boundary of what the Schrödinger equation permits. Now, and this is where things become genuinely vertiginous, both kinds of multiverse, if true, apply simultaneously. If eternal inflation is correct, and if many worlds is correct, then the structure of reality looks something like this. There is an eternally inflating, background-generating bubble universes. Each bubble settles into a vacuum state and develops its own physics. In each bubble, quantum mechanics governs the evolution of matter. In each bubble, every quantum event branches the local wave function into a new set of parallel histories. The total structure of reality is the collection of all branches across all bubbles, across all of eternal inflation, an infinite nest of infinities, each layer more vast than the one below it. Everett called his proposal the relative state formulation. His thesis advisor, John Wheeler, initially supported it and then distanced himself. The physics community largely ignored it for decades. But in the 1990s and 2000s, a combination of advances in quantum computing, which requires thinking seriously about quantum superpositions, and growing dissatisfaction with the Copenhagen interpretation's hand-waving, led to a significant revival of interest. Today, many worlds is taken seriously by a substantial minority of physicists and some polls of working physicists, though polls of physicists mean less than one might think, show it as the plurality view on quantum interpretation. Whether it's correct is a separate question from whether it's coherent. And one of the deep objections to many worlds is that it appears, on the face of it, to be unfalsifiable. If all branches are equally real and no branch can observe another, how could you ever test the claim? The answer, according to its proponents, is that you already test it constantly. Every experiment in quantum mechanics tests the Schrödinger equation, which is the core of the many worlds picture. The question is not whether the equation is right. It is to extraordinary precision, but what it means. And meaning in physics is tested indirectly through the consistency and predictive power of the interpretation's consequences. But there's another deep objection that deserves attention because it reveals something important about the structure of the many worlds picture. If all branches are equally real, why do we experience probabilities? In standard quantum mechanics, the Born rule tells you the probability of each measurement outcome. It's proportional to the square of the wave function's amplitude for that outcome. This rule works extraordinarily well. Every experiment confirms it. But in many worlds, every outcome happens. Every branch is real. So what does it even mean to say one outcome is more probable than another? Where do the probabilities come from? This is the probability problem in many worlds, and it is genuinely hard. Several approaches have been proposed. The most promising, developed by physicist David Deutsch and later extended by David Wallace, argues that probability in many worlds should be understood through decision theory, that a rational agent facing a quantum branching event should act as if the Born rule probabilities are real, because any other decision strategy leads to demonstrably worse outcomes even from within the many worlds framework. It's an elegant argument. Not everyone is convinced. What is clear is that the many worlds interpretation takes quantum mechanics with absolute seriousness. It refuses to add anything to the Schrödinger equation. It refuses to invoke a mysterious collapse process. It takes the mathematics at face value and accepts the consequences, however strange. And the consequences are a universe, a wave function of literally infinite richness, branching with every quantum event. Every branch as real as the one you currently inhabit. There is something profound about that. Not reassuring exactly, but profound. Every decision you make, every random event in your life, every moment in which things could have gone differently, in the many worlds picture, they did. There is a branch in which every possible outcome of every quantum event in your history was realized. There is a version of you for whom every coin flip went heads. There is a version in which the photon took the other path. There is a version in which the radioactive nucleus in a distant star decayed 1 second earlier, and the wave of particles that resulted reached a planet with life. and altered the history of that life in ways that cascade across billions of years. All of it real, all of it happening, all of it inaccessible from here. The edge of the many worlds multiverse is not a place. It is the totality of what quantum mechanics permits. But let's step back from the philosophical weeds. Because the many worlds multiverse, the eternal inflation multiverse, and the string landscape together constitute the current best answer theoretical physics can offer to the question, what is beyond the observable universe? The answer is more. Vastly, incomprehensibly, infinitely more. More space, more bubbles, more branches, more physics, more versions of reality than can be meaningfully counted or imagined. But none of. This tells us what is at the furthest possible reach of everything. Because all of these pictures, eternal inflation, the landscape, many worlds, are still embedded in something. They all presuppose a mathematical structure. They all assume that mathematics describes reality, which brings us to the strangest idea of all: the Level 4 multiverse. Max Tegmark, a cosmologist at MIT, has proposed what he calls the mathematical universe hypothesis. The idea that physical reality just is mathematical structure. Not that the universe can be described by mathematics, which is the usual physicist's claim, but that the universe is mathematics. That there is no distinction between physical existence and mathematical existence. Every consistent mathematical structure exists, not as an abstract Platonic form, but as a physical reality, a universe inhabited by observers who experience it. Under this hypothesis, the question, why does the universe exist, has a different kind of answer. The universe exists because mathematical structures exist, and mathematical structures don't need a cause. They are necessary truths. 2 + 2 = 4 in every possible universe, including universes in which nothing else exists. Mathematical structure is the one thing that truly exists without cause, without prior condition, without anything outside it that brought it into being. If the mathematical universe hypothesis is correct, then what is at the edge of the universe is not space, not vacuum, not another physics. It's the boundary of a mathematical structure, and beyond it are other mathematical structures, equally real, equally physical, inhabited by observers who are asking the same questions we are. Most physicists find this either deeply compelling or deeply unsatisfying, with very few in the middle. But it represents the outer edge of what theoretical cosmology currently entertains as a serious possibility, and it gives an answer to, why is there something rather than nothing that is at least internally coherent? There is something rather than nothing because mathematical structure cannot fail to exist, and physical reality is mathematical structure. We may never know if any of this is true. But the fact that it can be thought, that the human mind can reach from a rock on a small planet orbiting an average star in one galaxy among 2 trillion, and construct a framework that attempts to encompass all possible physical reality, is itself one of the most extraordinary things about the universe we find ourselves in. Chapter 7: The Far Future. What happens at the end of time? We've been talking about the edge of the universe in space, about what lies beyond our horizon in the vast unobservable reaches of the cosmos. But there's another kind of edge, a temporal edge, an end not just to what we can see, but to what can exist. What happens at the very end of time? This is not a question about the edge of space. It's a question about the ultimate fate of the universe, about what happens when the expansion has been going on long enough, when the stars have burned out, when the galaxies have gone dark, when even the black holes have evaporated. What is left? What is the final state of everything? The answer depends on which future scenario turns out to be correct. And there are several candidates, each stranger than the last. The first and currently most favored scenario, given what we know about dark energy, is called the heat death, or more precisely, the Big Freeze. In the Big Freeze, the universe continues to expand forever, driven by the cosmological constant. The expansion is not fast enough to tear apart galaxies or solar systems. Gravity is strong enough at those scales to resist the expansion. But on larger scales, galaxy clusters separate. Galaxies outside our local group recede beyond the horizon permanently. The universe grows emptier and emptier. Over the next few trillion years, the stars burn out. Not simultaneously, different stars have different lifetimes, from a few million years for the most massive to trillions of years for the smallest red dwarfs. But eventually, all the hydrogen fuel in the universe is exhausted. The last stars dim and fade. The universe goes dark. What remains? Stellar remnants, white dwarfs, neutron stars, black holes. Cold, dark objects orbiting one another in dead galaxies, separated by the expanding void. But even these are not permanent. Over time scales of 10 to the 40 years or longer, a number so large that writing it out in full would require more digits than there are atoms in the observable universe, protons may decay. This is a prediction of grand unified theories, that the proton, the building block of atomic nuclei, is not actually stable. It will eventually decay into lighter particles, with a half-life that depends on which GUT is correct. We haven't detected proton decay yet. Experiments like Super Kamiokande in Japan have set the lower bound on the proton lifetime at around 10 to the 34 years for the most common decay channels. But most GUTs predict it happens eventually. If protons decay, then all ordinary matter, every white dwarf, every neutron star, every cold rock floating in the dark between dead galaxies, eventually dissolves. The solid remnants of stars become diffuse clouds of electrons and positrons, which slowly annihilate each other into photons. The photons redshift, stretching to longer and longer wavelengths as the universe expands, their energy approaching zero. What's left? Black holes. Black holes are the longest surviving objects in the universe, and even they are not eternal. Stephen Hawking showed in 1974 that black holes are not perfectly black. Due to quantum effects at the event horizon, the boundary beyond which nothing can escape, black holes slowly radiate energy in the form of thermal radiation, now called Hawking radiation. The process is extraordinarily slow. A stellar mass black hole has a Hawking radiation temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. It radiates so little energy that it is utterly swamped by the CMB, which currently has a temperature of about 2.7 Kelvin. But as the universe expands and the CMB cools, eventually the Hawking temperature exceeds the background, and the black hole begins to lose mass faster than it gains it. A stellar mass black hole evaporates over approximately 10 to the 67 years. A supermassive black hole, like the ones at the centers of galaxies, some of which have masses of billions of solar masses, would take around 10 to the 100 years. That is a 1 followed by 100 zeros, a Google years. But eventually, every black hole evaporates. And what does the evaporation produce? A final burst of high-energy radiation? A flash of Hawking radiation as the black hole's final mass energy is converted to photons and other particles. And then nothing. After the last black hole evaporates, after 10 to the 100 years, the universe contains almost nothing but an increasingly thin, cold, red-shifted bath of photons and the occasional scattered electron or positron, all moving apart from each other at enormous speeds in an expanding void. The temperature approaches absolute zero asymptotically. The density approaches zero. Entropy approaches its maximum. This is the heat death. Not heat in the sense of warmth, but heat in the thermodynamic sense, meaning maximum entropy, the state from which no useful work can ever again be extracted. The universe settles into a state of perfect, undifferentiated equilibrium. No gradients, no structure, no process, no time in any meaningful sense, because time only passes when something changes, and in a state of maximum entropy, nothing changes. But there is one more concept from thermodynamics that haunts the heat-death picture, and it was identified by Henri Poincaré in the 19th century. The Poincaré recurrence theorem states that any sufficiently large but finite system in a finite region of phase space will eventually return to a state arbitrarily close to its initial state, given enough time. The system doesn't have to be guided back. Statistical fluctuations will, eventually and inevitably, drive it there. Apply this to the universe. If the universe is finite in some sense, if the relevant degrees of freedom are bounded, then given sufficient time, a Poincaré recurrence will occur. The universe will spontaneously fluctuate from maximum entropy back toward a low entropy state, not because anything external pushed it, just because in a system with finite phase space, all configurations are eventually revisited. The recurrence time for something as large and complex as the observable universe is incomprehensibly vast, on the order of 10 to the 10 to the 117 years for a single recurrence. That number has more zeros than there are atoms in the observable universe. It dwarfs the Google year lifetime of the largest black holes the way the age of the universe dwarfs a single Planck time. But it's not infinite. And if the universe is eternal, and if the relevant phase space is finite, eventually, somewhere, sometime, the universe fluctuates back. A new low-entropy state emerges from the void, not from a prior cause, but from quantum statistics. A new Big Bang, in a sense, without a cause, or more likely a much smaller fluctuation, a single galaxy, a single star, a single Boltzmann brain, experiencing a brief, causeless moment of ordered complexity before dissolving back into the equilibrium from which it arose. This is the deep future of the heat-death universe. Not silence forever, but an infinite succession of extraordinarily rare fluctuations, each one a tiny temporary island of structure in an eternal sea of maximum entropy. And somewhere in that infinite succession, by sheer statistical necessity, every possible configuration of matter and energy will eventually occur. Here's where it gets strange again, because even after the heat death, even in an apparently empty maximum entropy universe, quantum mechanics doesn't switch off. In the vast, cold, empty future universe, quantum fluctuations continue. Virtual particles pop in and out of existence, as they always have. the vacuum seethes with its baseline quantum activity as it always has. And in an infinite amount of time, those quantum fluctuations will, on occasion, spontaneously produce a large fluctuation, one big enough to temporarily decrease entropy and create a low entropy pocket of matter and energy in the otherwise featureless void. Given infinite time, every possible fluctuation will occur, including fluctuations large enough to spontaneously produce a brain, a fully formed functional brain, complete with a lifetime of false memories, popping into existence from the quantum vacuum of the empty universe, having a brief moment of experience, and then dissolving back into nothing. This is the Boltzmann brain problem. Named after Ludwig Boltzmann, the 19th century physicist who first grappled with the statistical mechanics of entropy, the Boltzmann brain represents one of the deepest pathologies in cosmological thinking about the far future. In a sufficiently old, sufficiently empty universe, random quantum fluctuations will produce, overwhelmingly more often than they produce a genuine Big Bang, and 13.8 billion years of cosmic evolution, isolated pockets of apparent complexity, brains with false memories, briefly conscious observers who believe they have a history but don't. If the universe is infinitely old and approaches heat death asymptotically, the number of Boltzmann brains eventually overwhelms the number of ordinary observers who evolved in the usual way, which creates a problem. If you are a typical observer in such a universe, you are vastly more likely to be a Boltzmann brain than a genuine evolved observer. But your memories of a consistent physical world, of childhood, of learning physics, of watching this video, all of that is inconsistent with being a Boltzmann brain whose experiences are random. So you have evidence against being a Boltzmann brain, which means you have evidence against living in the kind of universe where Boltzmann brains dominate. Which means you have evidence against certain cosmological models of the far future. The Boltzmann brain problem is taken seriously as a constraint on cosmological models. A future universe that produces too many Boltzmann brains relative to ordinary observers is considered problematic, not because Boltzmann brains are impossible, but because their dominance would imply that no observer can trust their own experiences or memories, which would undermine the very act of doing science. This is the far future of the universe in the heat-death scenario, a nearly empty void, slowly cooling toward absolute zero, punctuated in the incomprehensibly distant future by the extremely rare flicker of a quantum fluctuation large enough to produce something briefly, arbitrarily complex, and then nothing again. But there are other possible futures, darker ones. The second scenario is the Big Rip. In the Big Rip, dark energy is not a cosmological constant, but a dynamical field whose energy density increases over time. If this is correct, and current measurements allow for it, though they don't require it, then the repulsive effect of dark energy grows stronger as the universe ages. Not gradually stronger, but eventually strong enough to overcome gravity at shorter and shorter scales. First, galaxy clusters are torn apart. Their gravity can no longer resist the accelerating expansion between their member galaxies. Then individual galaxies disrupt, then stellar systems, then planets, then atoms. At the very end, in the final moments of the Big Rip, the expansion is so violent that even atomic nuclei are torn apart, and the fabric of space-time itself is ripped to pieces. the universe ends in a finite time, perhaps in tens of billions of years, depending on the specific dark energy model, in an instant of infinite expansion rate. Everything that exists is destroyed, not just rearranged. Destroyed. Space-time itself is ripped apart. After the Big Rip, there is no after. There is no space in which an after could occur. The universe ceases to be. The third scenario is the Big Crunch. In the Big Crunch, the universe eventually stops expanding and begins to contract. This requires that the expansion slow down, reverse, and collapse, which in turn requires that dark energy not dominate, or that dark energy eventually changes sign. Current observations strongly disfavor this scenario, since dark energy appears to be accelerating the expansion rather than slowing it. But some models of modified gravity or dynamical dark energy allow for a future reversal. In the Big Crunch, the universe collapses back on itself over tens or hundreds of billions of years. The CMB temperature rises as the universe contracts. Galaxies collide and merge. Stars are destroyed. Black holes grow. Eventually, everything is compressed back into a state of incomprehensible density and temperature, a mirror image of the Big Bang, but in reverse. Does the Big Crunch lead to a new Big Bang? Some cyclic cosmological models, notably the ekpyrotic model developed by Paul Steinhardt and Neil Turok, propose exactly this. In ekpyrotic cosmology, the universe undergoes a cycle of expansion and contraction, with each crunch generating a new bang. The edge of the universe in time is not an endpoint, but a transition, the universe bouncing through an infinite series of cycles, each producing a new cosmic epoch. Whether this is correct, whether the universe is cyclic, or whether the current expansion is the universe's one and only attempt is not known. The ekpyrotic model makes some predictions that differ from standard inflation, and future CMB observations may be able to distinguish between them. The fourth scenario is the most recently proposed, and in some ways the most unsettling: vacuum decay. In quantum field theory, the vacuum, the ground state of the universe, the state of lowest possible energy, may not actually be the true ground state. It may be a false vacuum, a local minimum of energy, stable against small fluctuations, but not the global minimum. Like a ball sitting in a shallow bowl on a hillside, it's stable in the bowl, but if it receives a large enough kick, it rolls over the rim and falls to the valley below, which is the true minimum energy state. The Higgs boson, whose discovery at the Large Hadron Collider in 2012 was one of the great triumphs of experimental physics, has a mass that places it in a regime where the electroweak vacuum may be metastable, not stable, metastable. Stable against small perturbations, but vulnerable to quantum tunneling. The quantum mechanical process by which a system can tunnel through an energy barrier to a lower energy state without having enough energy to classically overcome it. If this is the case, then somewhere in the universe, at some random time and place, a quantum fluctuation could nucleate a bubble of true vacuum, a tiny region where the vacuum has tunneled to its true lower energy ground state. Inside that bubble, the laws of physics would be different. The fundamental constants, the masses of particles, the strengths of forces, would have different values determined by the true vacuum state. Those values would almost certainly be incompatible with the existence of atoms, molecules, chemistry, life. The bubble would expand outward at the speed of light. It would grow, engulfing everything in its path, converting the false vacuum of our universe to the true vacuum. There would be no warning. The bubble travels at the speed of light, so no signal could precede it. One moment you would be here. The next, not even the next moment, because the bubble's arrival would alter the physics that allows moments to exist, you would simply be converted, along with everything around you, into a universe with different physics in which nothing we recognize can exist. The conversion would propagate across the entire universe, 1 light year per year, unstoppably, until every last corner of the cosmos had been consumed. How likely is this? Current calculations suggest the electroweak vacuum's lifetime, if it is indeed metastable, is far longer than the current age of the universe, probably longer than 10 to the 100 years. But probability and certainty are different things, and the unease comes not from the magnitude of the risk, but from its nature. This is not a catastrophe that builds up, that gives warning, that can be prepared for. It is instantaneous and universal and complete. The edge of the universe in the vacuum decay scenario is not a place. It's an event, a traveling boundary between the physics that allows us to exist and the physics that doesn't. A spherical front of annihilation expanding at light speed, which may or may not already be on its way from some galaxy billions of light years away. We would never know until it arrived. Chapter 8. The last questions. Let's take a step back from the specifics, the Boltzmann brains, the Big Rip, the vacuum bubbles, and ask the meta question that all of this is really circling. What does it mean for the universe to have an edge? We've explored several versions of this question. There's the spatial edge, the edge of the observable universe, the cosmic horizon. There's the topological question, whether space loops back on itself or extends infinitely. There's the multiverse, whether our universe is one bubble among infinitely many, and what lies in the inflating background between them. There's the temporal edge, the end of time in the Big Freeze, the Big Rip, the vacuum decay. Each version of the question leads to a different kind of answer. And what's striking, when you survey them together, is that in almost no version of the question is the answer what most people intuitively expect. Most people, if asked what's at the edge of the universe, imagine something like this. You travel outward, further and further, and eventually you reach a wall, or a void, or a boundary where the stars stop and empty space begins. Something you could point at and say, that's it. That's where the universe ends and nothing begins. But none of the serious scientific answers look like this. If the universe is infinite, and flatness and inflation both point in that direction, then there is no edge, there is no furthest point. For any point you name, there is another point further out. The universe does not end. It continues forever, filled with matter and structure, and the results of 13.8 billion years of cosmic evolution replicated across distances that make our observable universe look like a single pixel in an image the size of a continent. If the universe is finite with a non-trivial topology, closed and connected back on itself, then there is still no edge. Just as the surface of a sphere has no edge, a finite closed universe has no boundary. It has a finite volume, but there is no point at which it ends and nothing begins. It simply connects. If eternal inflation is correct, then beyond our bubble is not nothing but something actively, explosively dynamic. The eternally inflating background, generating new bubbles, never stopping, with no edge in any meaningful spatial sense, because the space itself is being endlessly created. And if the mathematical universe hypothesis is correct, then the question, what is at the edge of the universe, is not even the right question. The right question is, what is at the edge of mathematical structure? And the answer is, other mathematical structures, each equally real, each equally physical. In every case, the answer to what is at the edge is not nothing. It's something strange and vast, and almost certainly incomprehensible from within our tiny corner of whatever is out there. But here's the thing I want to push on, because I think it's the most important and least discussed aspect of this entire question. We might be fundamentally limited, not just practically limited, not just limited by the speed of our rockets or the sensitivity of our telescopes. Fundamentally, in principle, permanently limited. There may be aspects of the universe's structure that are not just currently unknown, but unknowable. Not just beyond our current instruments, but beyond what any instrument or observation could ever reveal, because the relevant information is beyond the cosmic horizon, and no causal signal from there can ever reach us. This is a genuinely new situation for science. Science has always operated on the assumption that the universe is, in principle, knowable, that observations and experiments can, in principle, decide between competing theories. But a multiverse, by its nature, puts most of its content beyond any possible observation. A bubble universe beyond the horizon cannot be directly detected. The inflating background between bubbles cannot be probed. The other branches of the many worlds wave function are causally disconnected from us by decoherence. Does this mean the multiverse is not science? Some physicists say yes, that a theory which makes no testable predictions is not a scientific theory, and that the multiverse should be regarded as metaphysics, not physics. Others argue that the multiverse is an inevitable consequence of theories that do make testable predictions, inflation, quantum mechanics, and that we cannot simply discard the consequence because we find it unverifiable. That would be like refusing to believe in the far side of the moon because you haven't been there. The debate is real and ongoing and important, and it is not resolved. There is a related question that cuts even deeper, and it rarely gets the attention it deserves in popular science discussions of the multiverse and the universe's edge. Even within our observable universe, within the 93 billion light-year sphere of space, we can, in principle, detect. There are things we may never fully understand, not because we haven't tried, but because the information needed to understand them may simply not be accessible. The Big Bang singularity is the clearest example. General relativity predicts that the density and temperature of the early universe grow without limit as you approach the initial moment. At some point, the Planck scale, where quantum effects and gravity become equally important, our current theories break down entirely. They give infinite answers to finite questions. They stop working. What happened at or before the Planck time, the first 10 to the minus 43 seconds of the universe's existence, is genuinely unknown, not because we haven't measured it carefully enough, but because the physics we have is insufficient to describe it. A complete theory of quantum gravity, which does not yet exist, despite decades of effort on string theory, loop quantum gravity, and other approaches, would be needed to describe what happened in that first instant. And what happened in that first instant may determine what the universe is like on the largest scales, including whether it is infinite or finite, whether inflation occurred, what the initial conditions of the wave function of the universe were. We are trying to determine the shape of the universe from the inside, using instruments made of the universe, without access to the physics that set the whole thing up. It's a bit like trying to read the instruction manual for a machine using only parts of the machine itself, while the machine is running, and the instruction manual may have been written in a language the machine cannot generate. This is not a counsel of despair. It's a description of the frontier. Science has always operated at frontiers like this one, where the questions exceed the tools, where the tools are being built to answer the questions, where progress comes in unexpected ways from unexpected directions. The history of physics is full of moments where something seemed permanently unknowable and then wasn't. The internal structure of atoms, the composition of stars, the age of the universe, the existence of the CMB, the mass of the Higgs boson. Each of these was, at some point, considered beyond the reach of observation. Each of them yielded. The question is whether the structure of reality beyond our cosmic horizon will yield the same way. Whether some future theoretical insight, some mathematical discovery, some new observational signature we haven't thought of yet, will give us a window into the universe beyond the window we currently have. Nobody knows. And that not knowing is not a flaw in science. It is science's natural condition at the frontier. The edge of knowledge is always, by definition, where knowing stops and wondering begins. What it means for our question, what is at the edge of the universe, is that the honest answer has two tiers. The first tier is what we know. We know the observable universe extends about 46.5 billion light-years in every direction. We know it contains approximately 2 trillion galaxies. We know it is geometrically flat, to the limits of our measurement. We know it is accelerating in its expansion, driven by dark energy we don't fully understand. We know it began in an extremely hot, dense state about 13.8 billion years ago. We know the large-scale structure is a cosmic web of filaments and voids. We know the CMB is the oldest light we can detect. We know the future of the universe, if dark energy remains constant, is a slow dissipation into maximum entropy over incomprehensible timescales. These are extraordinary things to know. The fact that we know them at all, from a small planet, using instruments assembled in the last few decades, by the accumulated effort of generations of scientists, is one of the most remarkable achievements in the history of human civilization. The second tier is what we infer. Beyond the observable horizon, if inflation is correct, is more universe. Vastly more, probably infinitely more, with the same basic physics as ours. Beyond that, if eternal inflation is correct, are other bubble universes with potentially different physics. Beyond those, if the string landscape is populated, are an almost incomprehensible variety of physical realities. And woven through all of it, if quantum mechanics is universal, are the branching wave functions of every quantum event, every possible outcome of every possible measurement, each one equally real, each one a universe in the many worlds sense. The edge of the universe, if it has one, is somewhere in that second tier, and we may never reach it in either the physical or intellectual sense. But the reaching matters. The asking matters. The fact that a species that evolved to hunt and gather on a small plain in Africa 300,000 years ago has, in the geological blink of an eye, built instruments that see 13 billion light years, formulated theories that encompass the entire structure of space-time, and asked questions that probe the outermost boundaries of what can be known. That fact is not a small thing. It is arguably the most extraordinary thing that has ever happened in the observable universe. Conclusion: standing at the edge. Let me bring you back to the beginning. You asked what is at the very end of the universe. You expected maybe a dramatic answer, a wall of fire, a void of perfect darkness, something you could point at on a diagram and say, there. That's where it stops. Here's what we actually found. The observable universe ends at a horizon 46.5 billion light years away. Not a wall, but a limit of light travel time, a sphere of knowability centered on wherever you happen to be standing. Beyond that horizon, the universe almost certainly continues. In all likelihood, it continues for vastly longer than our observable bubble, possibly infinitely longer, in all directions. If inflation is right, our entire observable universe is a negligible fraction of the full universe, which is itself a negligible fraction of the eternal inflating background, which is itself one possible realization of physical law among a landscape of 10 to the 500 others, which is itself embedded in a mathematical structure that may be one among infinitely many. The universe doesn't end. Or if it does, the ending is so far beyond our reach, spatially, temporally, conceptually, that the word ending loses its meaning. And in time, the universe ends in one of several ways. A slow fade to maximum entropy and frozen darkness, a violent ripping of space-time apart, a collapse back to a crunch, or the silent conversion of everything we know into a different set of physics by a bubble of true vacuum already traveling toward us at the speed of light. In none of these endings is there a beyond. In none of them is there a somewhere else to go. What's at the edge of the universe? If the universe is infinite, nothing is at the edge because there is no edge. If the universe is finite and closed, nothing is at the edge because there is no edge, just a surface that connects back to itself. If the universe is one bubble among infinitely many, what's at the edge of our bubble is the eternally inflating background and other bubbles of different physics. If the universe ends in time, what's at the temporal edge is, depending on the scenario, a cold and empty equilibrium, a ripping of space-time, a crunch, or the converted void of a lower energy vacuum. None of these is what most people picture when they ask the question. All of them are stranger. All of them are, in their own way, more wondrous. Because the universe is not a box. It does not have a lid you can lift to look inside. It is not something you can stand outside of and survey. You are inside it. You are made of it. The atoms in your body were forged in the same processes that built the stars. The laws of physics that govern your neurons are the same laws that governed the Big Bang. You are not separate from the universe, looking at it from a safe distance. You are the universe, in a small corner, looking at itself. And from that small corner, with instruments built from metal and glass and silicone, over the course of a few remarkable centuries, the universe has managed to determine its own shape, its own age, its own composition, its own origin, and the broad strokes of its own fate. It has looked toward its own edges and mapped the cosmic horizon. It has detected the afterglow of its own birth. It has weighed the invisible dark matter and measured the repulsive dark energy. It has proposed, seriously and mathematically, the existence of infinitely many other versions of itself. The universe figured itself out, or started to. The second tier, the multiverse, the topology beyond the horizon, the nature of dark energy, the question of why the constants have the values they do, remains open. Genuinely, deeply, possibly permanently open. Which means the most honest answer to the question, what is at the very end of the universe, is not a location. It's a direction. The end of the universe is where our understanding runs out, and our understanding has been running outward in every direction at an accelerating pace for 400 years. There is no reason to believe it stops here. There is every reason to believe that what looks like the edge today is, from the vantage point of a century from now, just another stepping stone. We are not at the end of the universe. We are at the beginning of knowing what it is.